Okay, so in this lesson, you're going to be proving the isosceles triangle base theorem, the isosceles triangle vertex angle theorem, the isosceles triangle perpendicular bisector theorem, the altitude to congruent sides theorem, and the angle bisector to congruent sides theorem. So I'm going to walk you through how to get this done. Let me go ahead and walk through here. So the first thing they're telling you to do, you've got an isosceles triangle where CA and CB are congruent, and they're telling you to construct an altitude. Now, the reason that you give when you state it, you're going to state that you're going to place the altitude from vertex angle C down to point D, which you're going to place on AB. And the reason you're going to state in your proof that CD is an altitude of ACB. So then you're going to state that that is done by construction, okay? And then as this guy over here is saying, as you can see, he's saying right here that altitudes are perpendicular to bases, so that's the next thing I'd say, is that you end up with perpendicular. So what you have here is you have this side being congruent to that side, and then CD is congruent to itself. And because this then creates two triangles that are right triangles, you have the hypotenuse leg theorem. The two triangles are congruent to each other by HL theorem, right? And therefore, you're wanting to prove the triangle base theorem, which means that the base angles here are congruent. Or that, I'm sorry, we need to prove that the altitude to the base of an isosceles triangle bisects the base. So now you have congruent parts from A to D and D to B are congruent because they are corresponding or matching parts of congruent triangles. So you would say CPCTC. That's the reason there. Okay, so now the altitude to the base of a isosceles triangle bisects the vertex angle. So this proof is exactly the same. You start with a triangle like this, you construct the altitude, and then what you say is, okay, what we have here clearly is we have a right triangle, right? A pair of right triangles that are formed by this altitude, and then you can use the same hypotenuse leg theorem to prove that that pair of triangles are congruent to one another. And just like before we said, well, that means corresponding parts are congruent. So that would mean that this angle here, right, CA down to D, that angle, and this angle BC down to D, this angle here, so those two angles are congruent to each other, and that's by CPCTC again, and that is the isosceles triangle vertex angle theorem. Now you have the perpendicular bisector theorem. Now this one is a lot like what we just said. It's actually almost identical to the first one, where what you're doing is you're proving once again that this is, once you've constructed an altitude here from the vertex angle and you have CD in place, and then you go through the whole process of saying, okay, these two triangles are congruent to each other, again by HL. And then you've said, okay, well, these sides are then congruent to each other. Therefore, here's the next step. The only thing you really have to say, D must bisect segment AB. Now you have a perpendicular bisector. So clearly the altitude, the vertex altitude in an isosceles triangle is the perpendicular bisector of the base. And that is that theorem there. And that was what, the third one. Yep, perpendicular bisector. Okay, now you have the altitude to congruent sides theorem. So in this theorem it says, hey, if I draw the altitudes from one side to the other, then those altitudes are going to be congruent to one another. So now we're going to go ahead and take a look here. Imagine that you've drawn an altitude, right? But this time not from the vertex angle. Now from the base angles, you're going to draw an altitude over. Okay, it's going to come, in this case, like basically right up here. In fact, this might even be a 90-degree angle already, in which case that would be the altitude and this would be the altitude. But in any event, you draw the altitude, and what you're going to see is you're going to end up with some triangles. So let's just pretend for a minute that we split it right here because we drew an altitude. We'd have a right triangle here, right? that has a common base with the right triangle here. So now you have the hypotenuse in both these right triangles is the same segment from A to B, right? You'd have some point D and some point E over here, let's say. So AE and DB are your two altitudes. So what else do we have in common? Well, angle A is going to be congruent to angle B by the base angle theorem. So by hypotenuse angle, so in this triangle here that we bisected B with, A is going to be congruent to B by the base angle theorem. So this angle A in that triangle DB is, excuse me, sorry, angle A is congruent to angle B. So you have hypotenuse angle, and anyway, that proves these two triangles are congruent to each other, and then by CPCTC, the altitudes have to be congruent to each other. And that's true even if you have to draw the altitude like way out here to make it a 90-degree angle or whatever. Wherever you have to draw your altitude, it won't matter because you're using this as the this is the common angle. A and B are common in the two triangles, and this is the common side. So it's just base angle theorem for A and B, common side, then hypotenuse angle, and then CPCTC. So we always know that if you are creating altitudes to the congruent sides, that those altitudes are going to be congruent to one another. And then finally, you have the angle bisector to congruent sides theorem. Now this one has a few more steps. So what you're doing is you're taking this triangle here. Oh boy, here we go. You're going to bisect angle A, and you're going to bisect angle B. Well, to begin with, A and B you're going to show are congruent, and that means if they're congruent, that you have a common angle. So as I bisect angle A over here, angle B is part of this new triangle AEB, right? And as I bisect this angle over here, then angle A is an angle in ADB. So A and B, that's an angle that is congruent, right? They still are going to have the same common side here, right? They have a side in common here. And then the other thing that you're going to do is you're going to take a look at the other angles that's created. If I bisect angle A, I end up with two angles that are congruent to each other. And if I bisect B, two angles that are congruent to each other. And in fact, what I'm going to do is use the transitive property to say, if, let's call this angle 1 and angle 2. If 1 and 2 equals A, and 3 and 4 over here equals B, then 1 and 2 have to be equal to 3 and 4. And by the definition of a bisector, 1 has to be equal to 2, and 3 has to be equal to 4. So you can even write 1 plus 2 equals A, 3 plus 4 equals B, therefore A equals B. Since 1 equals 2, then we could say 2 plus 2 equals, same thing over here, since 3 equals 4, 4 plus 4. So the measure of angle, 2 times the measure of angle 2 is equal to 2 times the measure of angle 4. Divide them both by 2, and you'll show that angle 2 over here, this bisected angle, is congruent to angle 4, this bisected angle over here. Therefore, in your triangle, you have, A is congruent to B, this side is congruent to itself, and 2 would be congruent to 4. So by angle, side, angle, you now have triangles that are congruent when you bisect these angles. And if the triangles are congruent, therefore the corresponding or matching parts are congruent, so the angle bisectors are congruent, from B to D and A to E. Those are congruent. So, quite a little bit more in that last one, a little bit of arithmetic to do, but nothing too difficult. If you need help, let me know.